72 million bottles of Coca-Cola are produced every single day in the US alone. That's 840 bottles every second, 24 hours a day, 365 days a year. But here's the crazy part. All of this started with a pharmacist who accidentally created a headache medicine in 1886 and sold his recipe for just $2,300. Today, that same recipe generates $38 billion annually. Welcome to Process Nest. We're taking you inside the factory that turns this 138-year-old formula into the most consumed beverage on the planet. You'll witness machines that fill bottles faster than your eyes can follow and discover why they treat ordinary tap water with more precision than NASA uses to fuel rockets. The scale is absolutely mind-blowing, and the process is nothing like what you'd expect. In 1886, Dr. John Pemberton stirred together coca leaves, cola nuts, and vanilla extract in a three-legged brass kettle behind his Atlanta pharmacy. He wasn't trying to create the world's most valuable beverage. He simply wanted relief from his morphine addiction and chronic headaches. The resulting brown syrup tasted bitter and medicinal. Pemberton's bookkeeper, Frank Robinson, suggested adding carbonated water to make it more palatable. That fizzy mixture became the first Coca-Cola, initially sold as a brain tonic that promised to cure headaches, relieve exhaustion, and calm nerves. Pemberton sold just 9 glasses on the first day for 5 cents each. Struggling with debt and failing health, Pemberton gradually sold portions of his business. In 1888, Atlanta businessman Asa Candler acquired complete ownership for $2,300. Roughly $75,000 in today's money. Candler transformed the medicinal syrup into a mass-market refreshment, but the core recipe remained virtually unchanged. Today, that exact formula generates more revenue in a single day than Pemberton earned in his entire lifetime. The original recipe book, handwritten in Pemberton's careful script, sits in a climate-controlled vault. Only a handful of people have ever seen the complete formula, and the company maintains that fewer than 10 individuals worldwide know all the ingredients and their precise proportions. What makes this formula so powerful isn't exotic ingredients, it's the mathematical precision of flavor balancing. Each batch requires exact measurements down to fractions of ounces, creating a taste so consistent that blind taste tests show 94% accuracy in brand identification. Modern factories receive this concentrated essence in unmarked steel drums. But before it becomes the drink millions crave daily, ordinary municipal water must be transformed into something far more precise than nature ever intended. Water constitutes 89% of every Coca-Cola, making it the most critical ingredient despite being the most abundant. Municipal water varies wildly. Atlanta's water differs chemically from Chicago's, yet every Coca-Cola must taste identical regardless of location. The solution is industrial-scale water engineering that would impress nuclear power plant operators. Incoming water first encounters activated carbon filters the size of shipping containers, removing chlorine, organic compounds, and taste-affecting chemicals that municipal treatment leaves behind. Next comes reverse osmosis, a process that forces water through semi-permeable membranes under extreme pressure. These membranes have pores 0.0001 microns wide, smaller than viruses, bacteria, or dissolved minerals. But pure water tastes flat and lifeless. Coca-Cola's water engineers then rebuild the water molecule by molecule, adding back precise quantities of calcium, magnesium, potassium, and sodium. The proportions are measured in parts per million, calibrated to enhance the syrup's flavor profile while maintaining global consistency. Advanced spectroscopy equipment analyzes every batch, measuring 47 different parameters, including pH, alkalinity, hardness, and dissolved oxygen levels. Water that deviates from specifications by even 0.1% gets recycled through the treatment process until it achieves perfection. The engineering extends to temperature control. Water is maintained at exactly 35 degrees Fahrenheit throughout processing. Warmer water absorbs less CO2 during carbonation, while colder water can shock the syrup and alter flavor compounds. This scientifically reconstructed water then flows through food-grade stainless steel pipes toward mixing chambers where it will unite with the mysterious concentrate that gives Coca-Cola its soul. Witness the transformation of simple ingredients into liquid legend within stainless steel chambers that gleam like spacecraft interiors. The mixing floor reverberates with a deep, thrumming bass note. The sound of massive agitators spinning at 3,000 RPM, creating vortexes powerful enough to blend flavor compounds down to the molecular level. Computer-controlled pumps inject concentrate with mathematical precision, each gram measured to the thousandth. The carbonation chamber is where the real magic unfolds. Here, CO2 gas dissolves into the finished syrup under 30 pounds of pressure in chambers so cold they frost over within minutes. The temperature holds steady at exactly 32 degrees Fahrenheit. Any variation and the delicate balance shatters. Every bottle and can entering the facility faces a gauntlet more intense than military equipment inspection. Glass bottles undergo 14 separate examinations using cameras, lasers, and pressure sensors that detect flaws invisible to human eyes. Rejected bottles get immediately melted down and reformed. There are no second chances. The cleaning process resembles a car wash designed by chemists. Bottles rotate through stations that spray them with heated alkaline solutions, rinse them with deionized water, and sanitize them with ozone gas. Each bottle gets inverted and flooded with water heated to 180 degrees Fahrenheit, then dried with filtered air heated to 200 degrees Fahrenheit. Both containers then pass through vision systems equipped with 47 different inspection cameras. These systems photograph every surface from multiple angles, using artificial intelligence to identify scratches, dents, or contamination smaller than human hair. Labeling happens before filling to prevent moisture from affecting adhesive. High-speed applicators position labels with accuracy measured in fractions of millimeters while handling 2,400 containers per minute. The labels themselves contain 14 different security features, including special inks that change color under ultraviolet light. Final container inspection uses X-ray technology borrowed from airport security. These systems can detect glass fragments as small as 0.8 millimeters or metal particles weighing less than a paperclip. Any contamination triggers automatic ejection systems that remove affected containers in milliseconds. These spotless, perfectly labeled containers now race toward filling machines that operate faster than the human eye can track individual units. The filling floor resembles a high-tech race where 2,400 containers per minute race through stations operating with surgical precision. Each bottle or can spends exactly 2.7 seconds at the filling station, long enough for perfect measurement, short enough to maintain production speed. Filling machines use counterpressure technology that pre-pressurizes containers with CO2 before liquid entry. This prevents foaming and preserves carbonation levels during the high-speed process. Electronic sensors measure liquid levels to 0.1 millimeter accuracy, ensuring regulatory compliance and customer satisfaction. Temperature management requires industrial-scale refrigeration systems maintaining the beverage at 38 degrees Fahrenheit throughout filling. Capping operations happen in 0.8 seconds per container using servo-controlled machinery that applies exact torque specifications. Bottle caps get twisted to 18 inch-pounds of torque, tight enough to maintain seal integrity, loose enough to prevent glass breakage. Conceaming applies 340 pounds of pressure for exactly 0.6 seconds, creating hermetic seals rated for 2 years of shelf life. Quality control reaches obsessive levels with inspection points every 15 feet along production lines. Fill-level cameras photograph each container, while weight sensors verify correct volumes. Carbonation meters use ultrasonic technology to measure dissolved CO2 without opening containers. Leak detection systems spray every sealed container with pressurized air, while sensors monitor for even microscopic leaks. Containers losing more than 0.01% of internal pressure get immediately rejected. Successfully filled containers now move toward packaging systems designed to prepare millions of units for global distribution. Packaging operations transform individual containers into shipping-ready units using robotics that choreograph millions of movements daily. Automated systems group bottles into configurations optimized for different retail channels. 6-packs for convenience stores, 24-packs for grocery chains, and 32-packs for warehouse clubs. Cardboard packaging utilizes corrugated material engineered specifically for beverage transport. The cardboard undergoes 23 different strength tests, including compression resistance, moisture absorption, and impact protection. Glue application systems apply adhesive patterns calculated to provide maximum strength with minimum material usage. Shrink wrapping equipment operates at temperatures calibrated within 2-degree ranges. Too cool and the plastic won't shrink properly. Too hot and it damages container labels. Palletizing robots stack packages using algorithms that optimize weight distribution and transportation efficiency. These systems can build 47 different pallet configurations depending on destination requirements and shipping method constraints. Final inspection systems verify package integrity, code readability, and proper stacking before approving pallets for shipment. Automated wrapping equipment applies protective plastic film using controlled tension that secures loads without damaging packaging. Loading operations coordinate with logistics software that optimizes delivery routes and schedules. Refrigerated trucks maintain product temperature within 2-degree ranges during transport, using GPS tracking to monitor both location and thermal conditions throughout delivery. From Pemberton's kettle to global distribution, this manufacturing process transforms simple ingredients into 2.2 billion servings daily, reaching consumers in 200 countries through supply chains spanning 6 continents. The engineering behind your everyday Coca-Cola reveals industrial complexity most consumers never imagine. Subscribe to Process Nest for more investigations into the manufacturing marvels that create products you use daily. Drop your suggestions for our next factory investigation in the comments. We'll continue uncovering the fascinating processes that transform raw materials into consumer favorites. This is Process Nest, where everyday products reveal extraordinary engineering. Thanks for watching.